Before we start, hello everyone. Can you hear us? Can you see us?
I can hear you and see you, Thomas.
Okay. And do you see the shared screen?
Yeah. Yep. Also,
okay, there's a title page. Okay, so if you wish, there are only a few students here because we have this hybrid meeting and most of our colleagues are online. So I think more colleagues will log in. But if you wish, you can start.
Oh, well, we can wait for a couple minutes if you want. Just do you think we can? Or we can start?
Yeah, because we need to close at 2 p.m. Finishing with all the questions. So maybe we should start.
Okay, sure, no worry.
Okay.
I don't know. I just wanted to introduce a little the conferences, if it's okay with you.
Yeah, sure.
I don't know if it's okay. My camera is blocked. I don't know if it's.
Oh, we don't see you.
No, it's okay. It's okay.
Yeah. Okay, wait a minute, Matthew, because
it's not important, huh?
Yeah, but we try to allow you to.
Oh yeah, it's okay. Yeah, thank you. Perfect. Okay, so I can see that we have a lot of people, and Abai is here, I think.
So 38 attendees online.
41 in line. It's very good, very good. Okay, but let's start. If you ready on your side at BME?
Yes, we have.
Perfect.
So far, we have only 5 students and two of us, but we are expecting more students coming.
Okay, but they will come during my just welcoming speech. It's okay. We can start right now. Just actually, it will be very brief. Just to welcome everyone. So I am Mathieu Arquet, and academic director of the Executive Master on Digital Twins for Cities and Infrastructures. So thank you all for attending this first conference of the series. I just wanted to explain about the context of the conferences and take just a few minutes, provide you the context. In collaboration with ENPC in Paris, UPM in Madrid, BME in Budapest, and ITU in Istanbul, the fourth university, we started 2 months ago a new program, Executive Master on Digital Twins, with a first cohort of 19 enthusiastic learners, and they are with us today. So basically, this program is designed to provide all the essential bricks to develop a digital twins for infrastructures and cities. And it encompasses the courses programming with BIM, IoT, machine learning, data, smart cities, and so on. So it's kind of a wide range of topics. And to apply all this knowledge in the second semester, the students will have to develop a big, what we call capstone project, basically a digital twins or part of the digital twins, to apply all their knowledge. And to help them with that, the program is online, as you can see, but we will have a few events gathering on site, and we'll have 3 on-site events during the year in Madrid, Budapest, and in Paris to provide face-to-face interaction finally. And lastly, inside all this program, we have added this series of conferences, and we start them today. So this is a huge milestone for us also, with the objective of broadening the application scope of digital twins, given by experts from various fields, and to bridge theoretical knowledge with real-world application, and to show diversity of application of digital twins in the world. So that's it. I don't want to take more time, just to give you the big pictures, and you can visit our website if you have more information. Before handing over the microphone, just obviously a huge thanks for the organization team on the conference and communication with Jeremy Blayer and Lucia, and on BME side with Thomas. Obviously, thank you for hosting the first conferences. And finally, obviously, of course, a huge thanks to Attila to be the first lecturer in this series of conference, and I wish they will be very fruitful. So enjoy the lecture. That's it for me. I will now hand over the microphone to Abba, one of our 19 learners, to introduce today's conference. We will have the lecture by Attila at the end, some question and answer, classically, for 10 to 15 minutes at the end. Thanks again, all. I enjoyed the lectures. Abba, it's for you now.
Thank you, Matthew. Yeah. So first of all, I would like to introduce Attila. So Attila Joó is an associate professor with a rich background in numerical methods and information technology. His expertise span thin-wall structures, bridges, seismic design, and experimental testing. Apart from his academic role, he serves as a director of BME, Innovation Management and Cooperation Center, where he actively contributes to the development of startups and spin-outs. On the lecture that he's going to talk about today is centered around a remarkable 5-year research project that is aligned with the construction of the one-story bridge over the Danube, connecting Hungary and Slovakia. The project's primary objective was to craft a real-time digital twin model for this specific bridge while pioneering novel methodologies for digital twin applications. So, Attila, over to you, please.
Thank you very much for the possibility to have part of this conference series. And we really appreciate here at the BME that we can be the first one in this series. And I hope it will be an interesting presentation. I try to finish it in time. And after that, or meanwhile, even during the presentation, maybe you can have some questions, but at the end, there will be some possibility, of course. So let me start. I just arranged the screen here as well, and now you can see the shared screen and myself. So as it was introduced, I would like to talk about twins, digital twins, through my eyes, especially because I'm a structural engineer, and maybe there can be different definitions for digital twins depending on the roles, what you do, or what's your profession. Of course, it's not only just my work. We have a large team. The most intense names who were intensively worked on this topic can be seen here. Maybe I can say 3 just departments and 2 departments and 1 company or department of structural engineering. Of course, this kind of digital twins, there used to be a large IT background. That's why we work together with the Department of Automation and Applied Informatics and 1 company who we work together with the scanning. So let me start. I would like to start with a comparison because the long time ago, it was not so long, we had to define what is the beam, right? Nobody knows that. But, oh, it's 3D model, or actually what is the workflow of it, or it's a software solution, or what is it exactly? And now we have a new step, I think, in the construction industry is the digital twin. So maybe I would like to place this between 2. Okay, it may be halves. And if I want to be very, very simple, I would say the beam has 2 things, the 3D geometry and some data, right? We used to do it like building the constructional model of a bridge, building. We have a real geometry, the final geometry, maybe which goes to fabrication and so on. And we have some data, material properties, names of the structural members, and so on. So based on that, what can be the definition of the digital twin from my point of view? Actually, the basic idea is that the same. So we have to have same 3D geometry and some data as well. There can be several differences. Let's say 3. The first one, this digital twin depends on time, right? So we want to store and use any kind of information which correspond to the structure since the design table to the end of the life cycle. And that's why I made this integration mark and 100 years, because we designed the bridges for 100 years. And of course, there are two other specialties. Let's say what kind of geometry we have. And it can be different what was on the design table, because during the reaction of a bridge, of a structure, we may maybe change something in the geometry. So what we need, the final geometry, definitely the final one, and what kind of the data. And from my point of view, basically this is the most important thing, the most important difference. The BIM model is just for one time only a model. Of course, maybe you can take into account the scheduling of the reaction and so on. But now I would like to store any kind of structural data. And that would be my message at the end, that we can store in the BIM model some other structural monitoring data. We can store the scan geometry, and I will show you that we can do special explicit dynamic analysis, and we can use those information later as well. So if you know this main, that I think that the future for structural engineers is the digital twin. We can have much more engineering information than just the geometry and just the fabrication information as well. Of course, BIM is part of this digital twin, but I will show you how can we extend some information. So the basic idea can be seen on this slide, that we need the 3D geometry, the 3D model, and it can be several kinds of 3D geometry, because we can have a finite element model, constructional model, and so on. And that will be the base geometry. And we can store any other data, what we need. And it can be some strain gauges, even temperature, wind speed on a structure, on a bridge, and so on. And we can have a finite element simulation. I show ANSYS, and what I will show during the presentation, all of them are ANSYS simulations. So we can store all kind of structural information. And the last part will be how can we share this, and how can we make it easy to see a large data, because we have much more data, and we will have much more data than it used to. So if I see the life cycle of a bridge, and the example will be a bridge here, we have different steps until the end of the life of the structure. It starts on a design table, and we can manufacture the thing. We can. May I ask you to turn on the microphone, please? Just 1 second. Okay, thank you. So the design table, manufacturing, the assembly erection phase we used to have in Hungary. I'm sure it's not all countries when there are proof testing of a bridge, but we have to do it here. And of course, the whole life cycle of the bridge. The basic idea, we will have some real measurements on the bridge, mainly strain gauges, which is most important for us from structural point of view. We will have finite element model for the different levels. We collect all those informations, because usually we use different softwares. We use different software for the design, maybe for different finite element models, depending if it's a global model or a local model, for making drawings during the manufacturing process as well, and even during the life cycle. Maybe we have a monitoring software as well. So we try to make this idea that we just have one model of the bridge, which will be now a Tekla beam model, which is a real geometry after the erection. And we try to store and extend somehow the functionality of the Tekla structures. And I will show you an application at the end of the presentation that helps us to reach all the information, even from the start to the end. That's why we call the invitation, you see, I wrote BOSS 5D. The BOSS is an abbreviation that bursts of steel structures, because the twins are born usually. So maybe that's the idea behind it. So why? And I think the construction industry is going through a large change, very effective change, according to the, let's say, car industry or mechanical engineering industry, where I'm sure you know about Industry 4.0. Now we can say that in the construction industry, we are in the stage of construction 4.0. So we try to use the digital technologies, technology all around the different phases of the design, erection, and through the life cycle of a structure. And those information and digital twins can be used plenty of places. We can, for example, if a bridge, usually we have a maintenance cost, we can have an extreme load. But if we know what's the real behavior in real time, maybe we can make more safer structures, and we can reduce somehow the maintenance cost as well. And I would say, as you heard in the introduction, I'm the head of the Innovation Management and Cooperation Centers. So I try to think on the business development side as well. What we have seen before in the previous slide, that we have usually nowadays, we have a company for design, company for the manufacturing, one company for the erection, and somebody will take care of the bridge in the whole life. So they are the different companies, and the information flow is not so easy between them. So it can be a new business opportunity, in my point of view, that these innovation technologies, and especially the digital twin, can be a new feature for new businesses as well. That's why this name here as well. So what we have now, I don't want to go into details, but as I mentioned, we have different softwares, we have different companies, even in the university. I will show you just some examples for these different phases. For example, the design phase. Again, I don't want to go into details, but we are using 3D models, maybe a BIM model as well. We are using some kind of finite element models as well for the manufacturing. We can do welding simulation. You can see a video on the right side on the 4 videos here, very simple welding simulation. So we can get any kind of information from those simulations. During the assembly erection phases, we can use geometry measurement tools, laser scanning, or we can monitor the behavior of the bridge as well, which is a usual thing, and we used to do here in Hungary and Budapest as well. We have nice bridges around Budapest. As I mentioned, we have to do proof testing of a bridge every time before they give it to the public use. For those, we also have finite element model, maybe different one that we use for the design, because it should be independent, and we just compare the result deflection for a specific load as well. And during the service state, we can have some, again, strain gauges, measure the displacement of the bearings, measure acceleration to define the vibration properties of a bridge. And maybe you know the structural health monitoring systems. There are independent research field on SHM where you try to judge the behavior of the bridge based on several sensor data. You can have accelerometers in every span, maybe 3 direction. You can have some strain gauges and so on. It can be one way to try to follow the real behavior of the bridge, but we want to improve that, and that's the digital twin, I think, and we will go further based on that. So as I mentioned, we have all these things actually, but the digital twin can be the one technology which connects each steps from the design to until the whole life cycle of the bridge. And the benchmark, what I will show you, the new results we have, it's Komárom Bridge. You can see the Hungarian map here, and this red sign. There is the Danube River, and there is a bridge between Slovakia and Hungary, the country north from Hungary. You can see the pylon here. The whole length of the bridge is 600 meters. The pylon height is 80 meters, and the largest span is 252 meters. And you can see some pictures from site and during the construction. So in the last 4 years, we had the chance that we had a project, and we were able to follow these steps. Actually, from the very beginning, we had the design data, the design drawings, we had the calculations for design the bridge, and we were able to follow it until the end of the reaction and during the service state as well. So based on the same steps, I would like to show you now the new results, what we have. And as I mentioned, we should have the final geometry of the bridge. Now it's a technical structure, it's a 3-dimensional constructional model. We have every plate and every welding can be found in the model. Of course, there were several finite element models was used during the design. It can be a simple beam model where we have beam elements left side, in the right side, maybe a complex shell and beam element as well, where the deck plate is usually made of shell finite elements, maybe the pylon as well, and maybe the cables are link or beam elements as well. These models were used for the design, but it can be used later with slight changes. I will explain it later during the presentation. We had the chance to be part of the manufacturing steps. So I just want to show you some details of the welding simulation, because we did some measurements on site, but maybe the welding preparation and defining the welding steps and choose the correct methodology for welding such a large structure. The welding simulation can be very useful. It can be a complex analysis. It's thermodynamic analysis where you can see the heat flow, and then we can do a mechanical analysis, and we can define the deformations, the strains, and the residual stresses as well. I just show you some examples. How can we do it in volume, finite elements, and even during the project, we developed a simplified welding simulation as well, because sometimes it can be very time-consuming, computer consuming to do this kind of simulation. But we can do it, and as I mentioned, we were able to measure during the fabrication process as well. Here you can see an example, an orthotropic deck you can see the method, the steps, how they fabricate this deck, how they pre-stress the plate itself, the orthotropic beams are, and the welding goes through. At the end of the manufacturing process and the simulation as well, we will be able to define the stresses on the members and the elements and the final geometry as well. Maybe it's not so clear, but here on the form these stresses where the welding are going in a longitudinal direction, you can see the stress concentration over there, which can be used later for engineering purposes, because we know the real residual stress in the structure. And as I mentioned, it for digital twin and the real-time digital twin, it can be a huge step that we know all the information from the fabrication. So not just only the time when the erection is finished and we start the life cycle of the bridge, but from the manufacturing process as well. So let's go to the next phase, the manufacturing. One, you can see that how we measure the strains on this orthotropic deck. And I have tons of pictures and reports as well. We measure different parts of the bridge as well. You can see a cross girder on the bottom right side as well. So we did plenty of strain and residual stress measurement as well. We also tried a new technology which is in the research phase right now. We try to measure the strains with a camera, resolution camera. We paint the steel structures with very small dots, and we, based on the movement of that strain nodes, so we can measure the strains in a very high definition camera, and it's a very useful technology as well. And as I mentioned, we just not measure the stresses by strain gauges, but we scanned the geometry as well. You can see in the manufacturing company whole how we measure the orthotropic deck and other parts of them. And these results can be used later, because given that this assembly can be found in the manufacturing place as well, because we can have a deviation map. So we can calculate the difference between the geometry we have in Tekla structures. We have the exact geometry what we would like to achieve, and we can measure, scan in every point, in every millimeter or so, the geometry, which gives us a much more information that we used to have, because usually in the classic technology, for example, for the deck plate, you just measure the corners, the edges, the cross girder main points. So if you used to have several points information, but with this kind of technology, which is somehow close to the 3D technology that we want to use in the digital twin, we can have much more and valuable information. We can do this, of course, during the assembly and the reaction phases as well. For this bridge, there were smaller assemblies prepared in actually different countries, Slovakia, Czech Republic, and Poland as well. And some of them, the deck plates part came to Hungary, and there was a pre-assembly phase here in Budapest, and then the whole deck plate went to the site. So this kind of measurement, because we have some extra welding during this pre-assembly phase and during the erection phase, we can do and define the residual stresses as well. And of course, we can measure the geometry, the same technology as we used in the industrial hall as well. We can do it inside as well to check the geometry of the bridge. So we are going closer to the service state, but before the service, we have to do the proof testing. You can see a picture of this site testing on the top right corner. The vehicles we have, of course, they are loaded, and we calculate the deformation by your own finite element model, the geometry, and the deflection of the bridge, and we do measurement as well with the geodesic technology. And on the bottom right graph, you can see two sides of the bridge in two lanes we used to measure, and you can see a very good agreement. Actually, there are two red lines and two blue lines, right? They are so close to each other that there is no problem with the bridge. So we measured what was the calculated shape of the bridge as well. And now I think we are coming to the most interesting part. And as I mentioned, based on the sensor data, there are independent research field about structural health monitoring. So we have to, or if you want to use SHM, then you want to decide the behavior of the bridge on several data. Of course, you have to install a monitoring system, but I think that the main problem with this kind of SHM technology, you will have information just from specific points of the structure. So you won't see the whole pictures. And I think that's why the real-time digital twin can be much more important for structural engineers. Because as soon as we have a monitoring system, maybe if we place the strain gauges in a special way, I will show you on the next slide, then we will be able to define the load. And actually, if we want to calculate the real behavior of the bridge, we have to know what's the load, the vehicle axle load which is going through the bridge. So I will show you how can we calculate it. How can we define the load which is going through every day, every minute on the bridge? After that, as soon as we have this kind of information, we can do an explicit dynamic, so real-time dynamic analysis. Just we have to know what's the exact load there. And as soon as we have this kind of simulation, we will know all the structural data as we need in all the points of the structure, not just only those nodes where I have sensors, strain gauges, accelerometers, and so on, but in all the nodes of the structure. So that's why I say the real-time digital twin can be much more useful for structural engineers. If I want to define it and do this kind of explicit dynamic analysis, I need some kind of input. As I mentioned, the input data will be some strain gauges. You can see a strain gauge on the picture. As soon as I define the load, I can execute an explicit dynamic analysis. I will show you some ANSYS figures or videos about that. And after that, I will have all the information in the finite element. The problem, just I have to export those data. Because as I started for the real-time digital twin, I would like to have just one 3D model. And I would like to store all kind of information, like explicit dynamic analysis information in that 3D BIM model as well. So we have to export that data, and that will be the output of this explicit dynamic analysis, and we will use backlog to show those information as well. So here are the measurement we have. You can see a photo of the deck plate on the bottom left side. And if we put strain gauges below the lanes where the vehicle goes, You can see here the red dots on the deck plate drawing in the cross section. We can have a specific information. Even if we place those strain gauges in two cross sections, you can see the small red lines on the side view of the bridge. We will be able to define the vehicle axle. It's not so easy. You can see on the right side, we can use finite element model for defining the impact surface. You could place 1 kilonewton of load, and we can collect all the measured stresses which where we have these strain gauges. So it's a, let's say, preliminary calculation. But after that, we will have real-time stress information about those strain gauges. You can see some examples, the stress, the distribution, the function of the time. So you can imagine we have a vehicle, 2-axle, simple car, 3, 4 axles, heavy trucks, and so on. They are going through the bridge. I have a stress distribution and plenty of them. It's hard to say that if the stress here is, let's say, 130, 1.5 Newton over meter square, then the vehicle load is this. So what we did, we applied AI, artificial intelligence, and a deep learning algorithm based on large amount of data, based on the time and plenty of strain gauge measurement, to calculate backwards the load. And you can see some workflow of this kind of AI and deep learning algorithm. We have to define this kind of stress concentration. You can see there stress changes during the time. Of course, we have to eliminate the noise. Based on the two sections, we are able to define the speed, the number of axles, the sum weight, the total weight of the structure, and after that we will have the axle weight. As I mentioned, we have the big data here. There are no exact solution, but a deep learning algorithm can be used, and it's a very effective way. Because the system, I think it's kind of cheap compared to other structures, but we have very much more additional value in it, because we have to develop this kind of artificial intelligence, and we can say the accuracy is much better what we have on the system that it's available nowadays. So who is afraid of the AI, based on this, actually myself, we can use it on plenty ways. And in the structural engineering industry and construction industry also can be a very useful thing in some cases. So as soon as we calculated and defined the axle loads which are going through the bridge, we can have an explicit dynamic analysis. You can see, or you will see a video, it started automatically, maybe you can see some slide changes in the displacement. We made some tests in small deck plate elements, how we place the vehicle, what will be the interaction between them, and you can see the time-dependent displacement of the deck plate, of the vehicle. So it's a real dynamic system. You can see the vehicle goes through, and it will change the stress fields in the deck plate as well here. Of course, we can do it in the whole bridge as well. Now we had some results on shell model, and now we are developing a beam model, which can be less time consuming to run this kind of explicit dynamic analysis, but we are able to calculate all kind of structural information based on the explicit dynamic analysis. At the end, If we have this data, then we have to show it somehow. As I mentioned, the BIM structural softwares, what we used to do, they are prepared to have manufacturing information, drawings, lists, and so on. So we have to develop our own application which can store this kind of data. It can be a sensor data, it can be a laser scan geometry, it can be a finite element simulation as well, and all of these depends on the time as well. So you can see what kind of data we can have. I just go to the next slide because I have a video and I want to show this. It works actually in Attila app. This is a simple structural example. We can have objects. We can define them as sensors, and you can see that we can store the sensor data. Of course, we can use timestamp data for those, and we can show, of course, the results. We have a tool, the down, you can see the colorful stripes. Those are the different sensor data and the time. It can be information from the manufacturing. For example, now you will see a weld simulation. It was done in ANSYS, the finite element software, and now it's implemented in Tekla, but we can add timestamp. So from the starting of the manufacturing process, we can have information and store it in a BIM model. If we have a sensor, we can do. And one extra tool, of course, we want to use this information later. So we have a Python interface because engineers maybe need those information, and that will be the future, I think. So we develop this interface as well. And I show you the not so far future. It's a HoloLens application, because as soon as we have the Tekla, the 3D model there, actually we can use AR and augmented reality to show the same. You can see the timeline here. You can see the same sensor data as well, and you can use your hand. I think the future, you can go outside the site to visit the bridge, and or imagination or vision for the future is that if a car going through the bridge, you have the sensors, you can, we will measure the strains, AI calculates the load, the explicit dynamic analysis will calculate the internal forces and stresses and deflection of the bridge, and it will be exported to Tekla, and you will be able to see the whole information of the bridge, structural information through a HoloLens. Of course, we are not there yet, but I think we are close, and we are closer and closer. This is one just an example that we can implement scanned information, the point cloud, into the Tekla BIM model as well. So as I mentioned, we are able to import all kinds of structural information into one model. So from a structural engineering point of view, what is the digital twin? And as I started with the comparison with the BIM and the digital twin, but actually it's not a comparison, because BIM is somehow part of it, because that can be the base geometry, but definitely from structural point of view, if you want real-time information about the bridge, we need monitoring system, extra measurements maybe, and we need an explicit dynamic analysis as well. So what should we do now? And I think I'm close to the end of the presentation, because what we do if we have this kind of real-time digital twin of the bridge. I think the opportunities are opening just right now, and maybe the young generation will be the key for this. From engineering point of view, of course, we have some experience, but this kind of the digital thing and the big data and the AI can be a very useful information, and it will define the future of the structural engineering. Just one example. As I mentioned, we have the Python interface. We can get the stress concentration from one field. And maybe, you know, if you want to calculate the static lifetime of detail, structural details, you have specific loads in the code, in the standard, which defines how have to define this kind of criteria for the bridge. And of course, the real load on the bridge is different. It's not the same. So you will be able to maybe extend, because usually the codes are on the safe side. So, but if you know the real axle load and you know the real stress distribution of the bridge, maybe you can extend the lifetime of the bridge. And maybe you can reduce, but not just maybe, but I'm sure we will be able to reduce the maintenance cost as well. So as I mentioned, we are working on this type of real-time digital twin. We are not there yet to get this final result, but all of the components and even much more than that are working, and I try to show you on this Komárom bridge example. So I hope you are not lost now somehow in the structural engineering point of view. Digital twins try to show you what's the construction 4.0 possibilities, how will the whole construction industry, even for structural engineers, will change, and how can we maybe develop new business models for this kind of model. So if you are not lost, you don't have to use this kind of virtual reality to be able to find a structural engineer, real-time digital twin model. So thank you for your attention.
Thank you very much, Attila, for your speech. Very, very interesting. I am a boot engineer myself, so it was very fascinating. I do have a lot of questions, but I am not the only one, and I'm not the first. So let's review. We have already one from Pachi in the chat. So I can read it. Do you use computer vision for monitoring the health of bridges during their service beyond other type of sensors? As example, for tracking cracks in concrete.
We are not using that. We know this kind of research directions, then how we can visualize or check this kind of cracks. I think that this kind of digital twins can be useful for this point of view as well, because as soon as I know all the structural data, I know I can calculate the static life cycle and crack propagation in every structural details. So I will know which one is the most critical one. And if I want to send a drone, let's say, below the bridge to find the crack, I will have the information that I don't have to scan for all parts and all details of the bridge, but I will have much more information to specify the most critical location. But we are not implementing this kind of visual checking yet. Thank you for the question.
We have another one with the thumbs up. The hand is up, so you can ask yourself the question.
Just check. Yeah, Hussainova, Azizga.
Hello, everyone. Thank you, Professor, for the presentation. If my voice is clear, I will ask one question. Is it okay? My
Yeah.
voice is all right?
Yes, thank you.
Yeah. So my question is actually about. I just want one thing clear in here, because I didn't quite understand that part. So using digital twin in bridge construction is only monitoring the bridge. So with those data, we will use those data in other bridge constructions, or we're just gonna repair some bridge problems with this digital twin?
Okay, thank you. And I think it's a very good question. I had no chance to talk about this, but what you've seen here is basically for one bridge and one digital twin. So now it helps to define problems on the bridge. However, and maybe that can be the next step and the future of the codes. Like if you want to improve the Eurocode, as soon as I know the real imperfections during the manufacture, I know the real residual stresses during the manufacture, I can have a safe structure, but maybe cheaper or more or a better design structure. If I have this kind of tool like digital twin, and I can concentrate on the structural behavior, maybe we can change somehow the safety margin we have. So at the end of the day, I think we will have a new design methodologies, and these kind of structural data, what we have from all kind of digital twins. If I may say an example in this digital world, the self-driving cars. And you have now one digital twin, one self-driving car, they have the measurement, they know how to drive. But as soon as you have 1,000, 100,000 self-driving cars, and you have all the data from those, you can build this kind of virtual world. You can extend the AI possibilities which drives the car. The same here. If we imagine that we have, I don't know, 9 bridges in Budapest, as I see out of the window, we would have 100-year information, digital information, 100-year experience for all of these bridges. The design method can be improved based on this real life example, I think. So that will be the future.
Okay, thank you. Got it.
Thank you. We have another one from Jeremy Blair.
Yes, thank you, Attila, for the very nice conference. I really liked it. So in fact, I have 2 questions. So the first one is a bit technical, let's say. So you're doing dynamic analysis. So often when we have dynamic behavior, we have some parameters which are not very well known, which are related to dissipation processes, etc., that would impact the damping of the bridge, etc. So in your talk, I assume that you have identified these parameters, but the fact that you have many ways of monitoring the behavior of the bridge, do you also plan to maybe improve this aspect of modeling damping and dissipation?
Yes, thank you. It's also a very good question. May I show you the proof testing slide? Just coming back here. We do this kind of validation, we can say, because this kind of site testing, what you see there on the slide on the bottom right, it's for fixed vehicle, no moving, no dynamic effect, right? But we used to do dynamic proof testing as well. Maybe on the left side, the one vehicle, the truck on the left side are doing this, moving different lanes, but we send through different trucks, 1, 2, 3, depends on the bridge, in different speed, slowly and increasing speed. And we will have the dynamic behavior of the bridge. We have accelerometer of the bridge, so we can use this kind of dynamic behaviors validation for the explicit dynamic analysis as well.
Okay, thank you. And the other question is about if you can comment a little bit on the maybe the difficulty of having all these different tools, numerical tools, communicating each other, passing information, exchanging, etc. So to make a a consistent numerical tool chain. So is it something which is really the piece that takes most of the time in developing a digital twin? And in that case, basically, what's the skills that the future engineers must have and must develop to make this technology more available in the future?
Yes, thank you. As I used to do, I have some of the guys sitting here. I always teach that. Always start the first lecture that the structural engineers need to have some programming skill as well, because I think without that we cannot improve the efficiency of the engineering, the whole construction industry and engineering industry. It's independent if you are sitting behind the desk and building finite element model. If you can develop an algorithm, we can make it easily, and the repeated words can be put for the computers or AI or anything, then it's the end of the day, it will be much more useful and efficient for engineers. This one's true for us. That's why we work together, as I mentioned, with the IT department as well. We need programmers, and it's a hard task. So it's not so easy, the communication, even if we have a large amount of data. So now we have, I think it's always a running contest that the computers are improving, the analysis will be more complicated. Simple linear ones, we increasing the numerical model, or we have a nonlinear simulation, or we have an explicit dynamic analysis, or we have a real-time dynamic analysis. And we need faster computers, need the data export, import, and transformation as well. I hope.
Yeah, thank you.
Thank you.
There is another one from Fouad in the chat, but mainly about what you said previously about, can the gathered data serve as a valuable resource for revising the design criteria for upcoming bridge projects?
Yes, I think absolutely. This is, I think, for the future part, as I mentioned, we will have more and more this kind of information. As I mentioned, imperfections, residual stresses, real behavior. So we will have much more exact information about the structural behaviors, and that's how the codes are improved, even for the beginning of the codes. If you have a new finite element tools, if you imagine very tangent rod, very simple design method, F over A. If we have a shelf finite element models and we have a stress concentration, you cannot design for the first yield phase. So we have to change the codes as well as the numerical models are improved. Yes, thank you. I think.
Yeah, thank you very much. I mean, I think we are nearly finished, and so 2 p.m. I just have one thing, comment, as you said, about new business, because you did your project like this on this bridge, but the question is, who is going to pay if we like do this kind of thing on all bridges? I mean, it's not so easy to find a collectivity, cities or whatever to pay for this kind of thing. They don't have the resources inside. They don't have the salaries with the skilled people to monitor this kind of thing. So it's a good question to create new business and new model about this thing, about all the digital twins applied for bridges, for instance.
Yeah, you're absolutely right. The economic is even these days not on the high level right now, but I think it can be an improvement, and you can have you can save some money. Of course, with investing, you can save, and even the government. If the building process, erection process, the service state, the whole life cycle can be cheaper, then it worth to invest to this kind of investment and money, because at the end of the day, you will have much more useful, exact, and cheaper information about the structure. I think it's a question for everywhere. Do you need a self-driving car? You have to invest cameras, right?
Yeah.
So it costs money, but if you see the advantage and you can convince the government, the builders, that it will have some advantage, then I think they are open to invest.
Yeah, I think I am already convinced. So, but the thing is sometimes, don't worry, but sometimes I do struggle to convince the cities or the owners of bridges to do these kind of things because they don't see on the short term, on the long run it's okay, but on the short run they don't see the advantages. But we have to be like how do you say, pedagogic. You have to explain nicely the outcomes. I think you need to leave the room at 2 p.m. Tamas told me.
Yes.
So
Tamas is here.
Yes.
Yeah. So thank you very much. I think we are going to end the session right now. No, Tamas, or do we?
Yes.
Do we have time for our last question?
Yes.
If you have a time for a last question, yeah.
Patchy has the last question.
Okay. If the future bridges maintenance based on data? Yes, I think both, in both cases, because you will have much more information even from the beginning. So the preventive maintenance can be specific because you have much more information. You don't have to have the preventive maintenance for the whole structure itself. You will have much more detailed information. And if you see a problem, you can see the problem coming maybe in a crack. So you will have a specific maintenance for the cracks as well, and you can find an easier way this kind of problems. Okay, thanks.
Okay, thank you so much. We are very proud that we could be the first presenters in this conference cycle. So besides or beyond the conference itself, think about us as potential partners in such research or educational cooperations. Okay, so that's what we are doing. We have multiple departments at our faculty. We are very open to digital twins and new technologies. So that's it. Happy to start this cycle.
Thank you again, BME, for hosting this first conference. A huge milestone for the master. Really appreciate that. And thanks all for attending the conference. You will find it recorded online. And the last words is to give you rendezvous in 2 weeks. The second conference will be hosted by ENPC in Paris on the 13th of December.
Great.
So see you then. Thanks a lot to everyone.
Bye-bye, see you.
Thank
And
you.
have a
Goodbye.
very nice day all.
Thank you.
Thank you very much.
Bye.
Bye-bye. Thank you.
Thank you. Bye-bye.
Thank you very much.
For coming.
Bye, everyone. Thank you.
Thank you. Bye.